Hey guys, here's a video on graphing and factoring polynomials. So last video we talked about graphing and factoring quadratics, and just to review that really quickly, we had examples like this: x squared plus 7x plus 10, and if we want to graph this, then we can consider how it's factored. It's factored as x plus 5, x plus 2. And once it's in factored form, it's easy for us to see the values of x that produce a 0. So we can see that a negative 5, if I plug it in here in place of x, a negative 5 will make a 0. Same thing with negative 2. If I plug in negative 2 in place of x, negative 2 plus 2 will make a 0. So those are the zeros of the function. And once we have those zeros, negative 5 and negative 2, we can graph it. And this is negative 5, and this is negative 2. Because it's a quadratic, we know it's going to look like a big smiley face. So that was the lesson we talked about last time. Here we're going to expand it to things that are a little bit bigger. So for example, let's keep this in factored form. Let's say you have something like this. Y equals x plus 1 times x plus 2 times x plus 3. Then we know that when we graph it, we're going to have roots at negative 1, negative 2, and negative 3. In other words, when the x value is negative 3, I'm going to plug it in for all of the x's, but this x right here, when I plug it into this x, is going to make a 0. And 1, 0 is enough that when we multiply it by these other things, it makes the whole thing 0. So we have those zeros. We have zeros at negative 3, negative 2, negative 1. In other words, those are the x values that'll be 0. So now the polynomial could go like this, or the polynomial could go like this. And so we have to consider the end behavior. So we'll talk about that in a second, but let's do another polynomial. What if we had something like this? Y equals x minus 4, x plus 2, x plus 3. Then when we graph it, we say negative 4, flip that to positive 4. Positive 2, flip that to negative 2. Positive 3, flip that to negative 3. And now we know it will cross the x-axis at those points. It'll have those x-intercepts, also called zeros, also called roots. And so it could look like this, or it could look like this. And we don't know. We'll have to look at the end behavior. Okay. So now we're going to skip to a discussion of end behavior. For end behavior, think of some kind of polynomial. Let's use this one. Let's say we've got this guy. We've got y equals x cubed plus 20x squared minus 70x plus 3. Okay. So now for this polynomial, I want you to imagine which of these terms has the most power. Imagine this is a tug of war, and you have 1, 2, 3, 4, and everyone is tugging in their own direction. So let me explain that a little bit more. The x values are constantly changing. So when the x value is equal to 0, let's consider the powers of these various terms. When x is 0 and we plug it into all of those terms, then what that's going to be is 0 plus 0 minus 0 plus 3. In that case, this guy is our most powerful term. But let's see what happens when x is equal to 1. Who has the most power now? Well, if we plug it into all these different terms, 1 cubed is going to be 1. 1 squared is 1 times 20 is 20. Negative 70 plus 3. Well, now this guy has the most power. In other words, the graph is going to be really negative when x is equal to 1 because of that term. So at negative 1, it's going to be really low and negative because that term is going to have the most influence at that point. Let's look at a couple others. Let's see what happens when x is equal to 10. So when x is equal to 10, we're going to plug that 10 into all of these places. We're going to plug it in all of those things. Now 10 to the third is going to be 1,000, so that's pretty powerful. 10 squared is 100 times 20 is going to be 2,000. If we plug it in here, that's going to be minus 700, and then we're going to be 3. So if you add up all those terms together, then you end up with a really big positive, mainly due to the second term. The second term is the most powerful. Now, the thing that I want you to really focus on right now is what happens when x approaches infinity and when x approaches negative infinity. Now, instead of using infinity, let's just think of a really scientific, precise number like a gazillion. Okay, I think that's how many zeros a gazillion has. So if you take a gazillion and you take a gazillion to the third power, then it's a gazillion times a gazillion times a gazillion. And that's going to be a ridiculously huge number. You can't even imagine how big that number is. And so when x is to the gajillion or the quadrillion, that to the third power is a lot bigger than the other terms. Let me convince you of that. First of all, it's definitely bigger than 3. Now, if you do 70 times a gazillion, you have 70 gazillions. Now, this one's a little bit trickier. A gazillion squared is a gazillion times a gazillion, and that's pretty big, and then times 20. But it's a lot smaller than a gazillion times a gazillion times a gazillion, right? Because a gazillion is bigger than 20. So when x is a gazillion, then this term is the most powerful. Now, why does that matter? It matters because if we have some equation like y equals x cubed, let's keep the same equation actually, plus 20x squared minus 70x plus 3, and we want to know how this thing behaves on the extremes at infinity and at negative infinity, it turns out that 3 is irrelevant, right? 3 is not going to be very big compared to the other terms. And for the same reason, this is going to be really small, and this even is going to be really small. The thing that's going to be way bigger than everything on the extremes is x cubed. And so that means when we're considering the end behavior, we only need to consider the first term. And what do I mean by end behavior? By end behavior, I mean, does it do something like this on the edges? Or does it do something like this on the edges? Or does it do something like this on the edges, right? So it's as you approach this way, you have a question mark. Are you going to go down or are you going to go up? Same thing, as your graph is moving along here and you get to infinity, are you going to be moving up or are you going to be moving down? And the end behavior is what answers that question. So with that as an introduction, let's talk about that same equation. Y equals x cubed minus or plus 20x squared minus 70x plus 3. Sorry, that's a cubed. Let me fix that. Okay, and again, like I said, when you're approaching infinity, when your x value is approaching infinity, the only one we're paying attention to is this one. And we're curious, as you get closer and closer to infinity, are you going up or are you going down? Let's think about this. If you have y equals, and we'll just use infinity for now, even though you can't really use it like this, we're going to do it anyway. Plus 20, we're going to forget about all those terms. So infinity cubed, so that's going to be infinity times infinity times infinity. And these are all positive, 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 positive. So this means as x approaches infinity, y approaches infinity. Now let's consider this on the negative side. So let's consider what happens when we approach it from negative infinity. So if I have a negative infinity, so x approaches negative infinity. So we're going to get this negative infinity and we're going to put it inside our equation. So that's going to make that negative infinity times negative infinity times negative infinity. And a negative make a positive, but a positive times a negative make a negative. So that means when x approaches negative infinity, y will also approach negative infinity. So let's connect that now graphically. Let's see if we can draw this picture and put it all together. So here's my graph. I don't know what it's doing in the middle. It depends on the tug of war between those various players. It could have all kinds of interesting shapes. But as I approach infinity, x, so this is infinity right here. This is my x value. So x is approaching infinity. As I'm getting further and further to the right, then the y value is going to positive infinity, and so it's going to zip off in that direction. Now, negative infinity is over here. As I get closer and closer to negative infinity, my y value is going to drop down to negative infinity. My y value is going down. Okay, so let's consider a couple more. What if you have something like this? X to the 6th plus 3x to the 5th minus 3x to the 4th plus 10. And we want to consider what happens as I get towards positive and negative infinity. So let's take a number. Let's just do some number like 1,000 or 10,000. So if we take 10,000, that's just kind of a stand-in for infinity, and we take 10,000 times 10,000 times 10,000 times 10,000 times 10,000 times 10,000 times 10,000, 10,000 to the 6th power, is that going to be positive or negative? And of course, it's going to be positive because it's a positive number. You're just multiplying it to the 6th power. That's going to be positive, and it's going to be a huge number, so it's going to be way up here. So no matter what wiggles you have going on, it's going to zip off in that direction. Now, what about this number right here, which is negative 10,000? If we get negative 10,000 and plug it into the equation, this one we have to think about a bit more carefully. Negative 10,000 to the 6th power. Well, that's going to be negative 10,000 times negative 10,000 times negative 10,000, negative 10,000, negative 10,000, negative 10,000. So negative negative is going to make a positive. Negative negative, positive. Oh, I drew one extra one. There we go. And we've got a negative negative, and that's going to make a positive. And so when we take a negative number and raise it to the 6th power, negative numbers to the 6th power are positive, and so that's going to end up going like that. Okay, so to sum up, if you have something like this, if you have x to the 2nd, x to the 4th, x to the 6th, x to the 8th, dot, 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 x to the even, then it's going to look like this. It's going to be wiggle, 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 like that. It'll be a big smiley face. And that makes sense, right? You remember quadratics. Quadratics are always smiley face. They go up on either end, because if you have like negative 100 and you square it, a negative times a negative is a positive. So as long as the exponent is even, then it's going to look like a smiley face. But I should say there's one trick, and the one trick is this. What if I have these ones? Negative x squared, negative x to the 4th, negative x to the 6th, negative x to the 8th, dot, 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 negative x to the even. Well, in this case, remember what negative quadratics look like? They end up having this kind of behavior. Well, quadratics are smooth, but they go like that. Okay, they're sad faces. They're sad. Look how sad that is. Okay, and why does that work? Let's just graph this really quick. Let's say we have 100, and we plug 100 into this equation. Well, the equation is negative x squared, so if we do negative 100 squared, that 100 squared, we do that squaring first. That's 100 times 100, and then we can't forget this negative sign, which we slap on there, and that makes negative 10,000. So this is going to make it sad on this side. And the same thing, if we plug in negative 100, and we do it inside there, negative 100 squared, negative times negative is a positive, so that's positive, but then we slap the negative sign on it, that flips it back to negative, so it's going to look like this. So, to recap, if you have x to the even, it's a smiley face. If you have negative x to the even, then it is a sad face. Okay, so those are even powers. Anything, and it doesn't matter, again, what follows it. So as long as it's x to the 12th plus 3x to the 7th minus 100 x to the 5th, ignore all of those. X to the 12th is going to have some wiggles, but overall its end behavior is going to be a smiley face. Okay, now let's talk about x to the odd. Okay, so we talked about x cubed. X cubed is going to look like this. As you go to the right, you're going to approach here, and as you go to the left, you're going to be here. Now, why is that? Again, if we do negative 100, and I plug it in here, negative 100 times negative 100 times negative 100, negative, 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 that positive, negative, that turns into a negative. So negative 100, if that's my input, if I input that into my equation and I cube it, a negative cubed is going to be negative. So that's going to end up wiggle, 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 and like that. So x to the odd. X to the odd will always look like this. They'll go down on the left, they'll go up on the right. Now, what if I have negative x to the odd? Well, if I have a negative x to the odd, like negative x to the 7th, then it's going to do the opposite. It's going to be like that. Okay. So that's everything. That's end behavior. Again, this is what I would jot down in your notes to remember. X to the even and negative x to the even. Okay, x to the even is going to be a smiley face. Negative x to the even is going to be a frowny face. Okay, so those are even exponents. And then finally, if we have x to the odd is going to look like this. And negative x to the odd is going to look like this in terms of the end behavior. Okay, that's everything you need to know about end behavior.